Hey there. We all feel like we have a pretty good handle on gravity, right? It's the thing that keeps our feet on the ground and the planets in their orbits. But what if I told you the truth is a whole lot weirder and way more beautiful? Today, we're going to tear up the old rulebook and find out what gravity really is. Let's get into it.
Seriously, just think about that for a second. What if there's no invisible rope pulling you down? No mysterious force reaching across the vast emptiness of space? What if that feeling of being pulled is just a misunderstanding, a side effect of the actual shape of reality itself?
This one sentence, right here, is the key to the whole thing. It's the core of Einstein's revolution. It completely flips the script. Instead of a force, it paints a picture of this incredible dance between matter and the very fabric of the cosmos. This is where our journey begins.
Now, to really appreciate just how game-changing Einstein's idea was, we have to look back at the problem he was wrestling with. For hundreds of years, gravity was basically a ghost in the machine.
Look, Isaac Newton's laws were amazing. They let us predict planetary orbits with mind-blowing accuracy. But even Newton himself was stumped by one thing. How did it work? How could the sun, millions of miles away, instantly pull on the Earth with nothing in between? It didn't make sense. It was just spooky.
So Einstein comes along, and he doesn't just tweak the rules of the game, he changes the entire playing field. He realized that space and time aren't just an empty stage for things to happen on. No, they're woven together into a single dynamic fabric, space-time. And gravity? Well, gravity is nothing more than the curves and dips in that fabric.
So if there's no force, why do things move? Well, in this new reality, objects are just doing what comes naturally. They're following the straightest possible path they can, and the name for that path is a geodesic. Simply put, a geodesic is just what straight means in whatever geometry you find yourself in. This makes it super clear. If you look at a flat map, the shortest way from New York to London is a straight line. But we know the Earth is round. So on a globe, the actual shortest path is a curve, what pilots call a great circle route. It looks bent to us on the flat map, but on the sphere, it's the straightest shot. A geodesic in spacetime is exactly like that flight path.
And this brings us right back to that famous apple. It's not being pulled down by some mysterious force. The Earth's massive weight has created a deep curve in the space-time around it. And the apple? It's just freely coasting along the straightest, most efficient path available in that curved space. What we call falling is actually the purest form of motion there is.
Okay, so how does mass actually do this warping? It all boils down to one fundamental idea. The universe has a master rulebook for how to measure distance. And gravity is just what happens when stuff like stars and planets gets to rewrite that rulebook.
In physics, this rulebook is called the metric. You can think of it as a universal formula, we'll just call it d squared for short, that tells you the distance between any two things, or any two events, in space-time. But here's the wild part. This rulebook isn't written in stone. Mass and energy literally change the formula from place to place. Out in the dead of empty space, the d-squared rules are simple and the same everywhere. It's like using a normal, rigid ruler. But get close to a massive star, and those rules get all twisted. The very definition of an inch or a second gets warped because the rulebook itself has changed.
And the consequences of this are just mind-bending. When the d-squared rules get warped near a massive object, time itself literally takes slower. Distances get stretched out, and as we've seen, the shortest path between 2 points, that geodesic, is no longer a straight line, but a curve.
Okay, all sounds pretty wild. I get it. But how do we know any of it is real? Well, because this crazy geometric idea makes some of the most precise and stunning predictions in all of science. Predictions that have been proven right again and again.
For decades, there was this tiny, unexplainable wobble in Mercury's orbit. Newton's laws just couldn't account for it. But when you plug the sun's mass into Einstein's equations, when you calculate how the d-squared rules are warped that close to the sun, you get a prediction for that wobble that is spot on. Perfect. It was the first time everyone realized, whoa, this theory really works.
And after that, the hits just kept on coming. In 1919, astronomers watched starlight literally bend as it passed the sun during an eclipse, exactly as predicted. In 1971, they flew ultra-precise atomic clocks on airplanes and proved that time really does run slower closer to Earth. And then, the big one. In 2015, we directly detected gravitational waves, the sound of space-time itself ringing like a drum.
So what are these waves? It's so important to get this right. They are not ripples moving through space. They are ripples of space. They are the d-squared rules themselves oscillating, stretching, and squeezing the very definition of distance as they pass by, all because of some cataclysmic event, like two black holes crashing into each other.
This chart really ties it all together, doesn't it? Every single major idea in general relativity, from the path an apple takes to the bending of light to ripples in the cosmos, it all comes back to the job being done by this master distance rule, d squared. The metric is the rule book, a geodesic is just the shortest path, and mass is the author of the whole thing.
Einstein's theory is just unbelievably successful. But like every great theory in science, it has its limits. It actually points to its own breakdown, right at the edge of what we can possibly know.
And that breakdown happens in a black hole. This is the ultimate stress test. It's where you have so much mass crammed into such a tiny space that the warping of the d-squared rules becomes completely overwhelming. It's geometry pushed to the absolute extreme.
Right at the heart of a black hole, the theory predicts what's called a singularity. It's a point where the curvature becomes infinite, and our entire rule book just fails. The d-squared formula breaks. The very ideas of here and there, of distance itself, they just stop making any sense at all. This is general relativity's way of telling us it's not the final story. It's a theory of big, smooth things. To really understand what's happening inside a black hole, or at the moment of the Big Bang, we need something new. We need a theory that combines gravity with quantum mechanics, a theory of quantum gravity. And so, that leaves us with this final, mind-melting question. Einstein gave us this beautiful picture. Gravity is geometry. But what happens at the quantum level, where things stop being certain and become fuzzy probabilities? What happens when the very shape of space, that master rulebook for distance, is no longer a fixed thing, but a shimmering cloud of possibilities? Answering that, well, that's the next great adventure in physics.